So this example, we're going to look at a polynomial with roots at -1/2 and at 3, and the 3 has a multiplicity of 2. In particular, so we're just going to work backwards. Since we know how to find roots, we're going to work backwards to find the polynomial. We know that x has to equal -1/2, and also x has to equal 3. So if I solve for x in each not solve for x, but let's move everything over so we get 0. So this is equal to 0. Now this will be equal to 0. So what I found is, we found the factors of our polynomial. Therefore, our polynomial is y equals x plus 1/2 times x minus 3. But remember, this had a multiplicity of 2, so this is to the second power. If I were to sketch this, so let's just get crazy, let's sketch this thing. We know this has to be within the family of the x cubes. How do I know that? Well, because this is to the first power, and now this is really x squared. So then if I multiply these two, that'll give me x to the cubed. Now let's look at this sign here. This is a positive sign, this is a positive sign, therefore this is also positive. So this is going to have the shape of x cubed. However, it's going to look kind of stretched out. What do I mean by that? Well, let's look. So I know that first of all my x-intercepts are at -1/2 and at 3. So therefore, my graph is going to start with the right side as it's shooting up. Okay, but then the thing is, I have a multiplicity of 2 at the x-intercept of 3. So that means it's going to shoot back up right away because it's bouncing off of that. And then next it's going to shoot back down, but then go through -1/2 only once. So therefore we have our graph of y equals x plus 1, y equals the quantity of x plus 1/2 times the quantity of x minus 3 cubed. Squared, not cubed, squared. Now we're going to talk about the intermediate value theorem. So the IVT states that let a and b be real numbers such that a is less than b, and if f is a continuous function and f of a is not equal to f of b, then in the interval a to b, f takes on every value between a and b, f of a and f of b. I know this sounds really, really difficult, so I'm going to show you guys what this means in terms of the picture. Let's say we have some, some points. So let's go with like 2, 3, and -4, -2. Okay, so that would be something like this. It would look something like this. Okay. I'm going to say that our function is continuous. So what does that mean if our function is continuous and it contains these points? That means these 2 points are somehow connected. I don't know what the graph looks like. I don't care. I just know that it's a continuous function and that it has these 2 points. Well, how does this relate to the intermediate value theorem? Well, so basically what I've said is, okay, I'm going to let this value be my A, this value be my B. So therefore this value right here is my f of b, and this value right here is my f of a. So that means that our curve does something really nice for us. So since we've satisfied that it's a continuous function and that our y values are not equal to each other, then that means within our interval a to b, so our x values, let's say like something over here, okay, then f will give me a y value for that corresponding x value. So there exists a point right there. Same thing with this, there's an x value there, therefore there exists a y value on this curve. Basically, the intermediate value theorem, its purpose is to tell you that you'll find a point anywhere in between this interval, no matter what, as long as your function is continuous and that our y values for our endpoints are not equal to each other, you always find a y value for some given x value between the values of the x interval. So let's look at this example here. We're asked to prove that our f of x function has a 0. I need to give you guys the f of x function. Let's try f of x equals 8x squared subtract 16x minus 1. So what does that look like? Well, I don't really care. I don't really want to find the x-intercept. All I want to do is prove that there exists one. So let's see, what's a good way to do this? Well, let's try this. So if I plug in f of 0, we get 0 minus 1, which gives us negative 1. If I plug in f of, let's say, 1, does that work? So that gives me 8 minus 16 minus 1, which gives us negative something. Negative 9. Okay. This is not going to work. So I picked two x values that aren't necessarily going to work, because if I take a look at my graph, so this gives me the point, the first one gives me a point of 0, comma, negative 1, 0, comma, negative 1, and the other one gives me 1, comma, negative 9. Okay, well, I want to find a 0, right? So, meaning it has to cross the x-axis. This right now doesn't help me because all I've done is said, okay, here are 2 points, and I know this is a continuous function because this is a polynomial. And remember, polynomials are always continuous and have a smooth curve. But even if I connect this doesn't go through the x-axis. So I need to find another point that does. So let's take a look at, it looks like it's going to cross over here somewhere. So let's pick a point further out in the negative direction. So let's pick like negative 10. Okay, so f at negative 10 will give us 800 minus 160 minus 1. That's something really big. What, 639? Okay, something like that. Okay, so that gives me, my graph is that point at negative 10, comma 639. It's going to be really high. I'm not going to actually sketch that, so it's going to look something like this. Now if I take the first point I chose and the last point I chose, and then once again, we know that this is a continuous curve because it's a polynomial. If I connect it, because it's continuous, I can do that. And because our y values are not the same, since this is negative 1 and this is 639, I know that this has some point between the x values such that it crosses the x axis. So the whole point, once again, of the IVT is it guarantees you that if you have a continuous function and that the y values are not equal, then you will always be able to find some point in between that interval such that you'll be given a corresponding y value.